today, so happy to chat with everyone about physics and any topics that come up either within the lectures or outside of the lectures. So broadly, the three lectures that I'm going to give, we've tried to coordinate a little bit between Dima, Professor Abon, and me myself, and we'll talk about a couple of topics that will kind of have a bunch of intertwined connections. Broadly speaking, today I'm going to try to introduce, on a pretty precise level, what it means for a quantum many-body system to thermalize. And maybe in the context of this lecture or the next lecture tomorrow morning, I'll describe what happens when that thermalization fails, which typically goes under now, these days, at least one of the classic examples, is many-body localization. And regardless, in some sense, of how far I get on these topics, on the last lecture on the third day, on Wednesday, I'll want to introduce some notion of flochet phases of matter. By that time, Professor Abon will have already introduced you to the nuances of periodically driven flochet systems. And in particular, in that lecture, I'll focus on the notion of time crystals, which is pretty active, has been pretty active in the last couple of years. So these lectures, at least, especially the first two, are based, there's already a number of really, really nice background references, and these lectures are very much based on them. There's a very nice annual reviews of condensed matter physics paper by Rahul Nandkishore and David Hughes back in 2015. A set of side post lecture notes by Antonello Scarpicchio and Thierry, slightly different Thierry, from a couple years ago, and a really nice review kind of on progress in Untitled Chapter by our very own Dima and Zlatko Popic. So the broad topic that I want to talk about today, the school is focused on quantum many-body systems, and the topic that we're going to focus on within my set of lectures is really on trying to understand the dynamics of quantum many-body systems in strongly interacting systems. And I think this topic kind of sits, I would say, at the interface of three kind of subfields of physics, that being quantum statistical mechanics, condensed matter physics, and AMO physics, especially on the experimental side. So one thing I want to put out just immediately is that much like some of the topics that you've been hearing about in the morning set of lectures, all of the physics that I'm going to be describing today really lives in the context of strongly interacting, strongly correlated many-body systems. But the difference from some of the things that were discussed in the morning sessions is that instead of focusing on the ground state and trying to understand what the low energy properties of a quantum many-body system are, here we're going to be interested in understanding the dynamical properties of that system at either finite energy density or in fact very high energy density. So really we're working in a regime that's far from the maybe typical context of condensed matter and trying to understand ground state bases of matter and working in a much higher energy density regime. Sometimes we'll even be talking about physics at infinite temperature. But the one thing, despite the fact that all of these systems are strongly interacting, strongly correlated, the maybe most important caveat about thinking about the physics that I'm going to be describing is the fact that the context is really in very well isolated systems. So we really want to be thinking about, at least for the physics that I'll be talking about, systems that are isolated from a bath. So oftentimes when we think about quantum statistical mechanics or stat mech in general, we have this notion of coupling to a bath that defines a notion of temperature. Right? Exchange with the bath, whether it's particles or energy density, helps to define equilibration, this notion of thermal quantities, for example. But here, we're really going to be thinking about isolated quantum many-body systems. And in that particular context, I really think that many of the platforms that we have in atomic, molecular, and optical physics are really particularly well suited to study and to explore some of the physics that I'll be talking about, especially in the experimental context. So on Thursday and Friday, I think Emmanuel will be telling you about some of the pioneering experiments done in his group on looking at in experimental systems and in regimes outside of what we can really understand, looking at the phenomenology of many-body localization and the failure of quantum thermalization. Good. So with this little bit of background, we're going to be interested in two, please call out, so I guess I'm both, perhaps it's bravery, perhaps it's folly, but I've decided to lecture on the board, as you can see, so please call out with questions. You'll get my lecture notes online, and I don't expect to cover everything in my lecture notes, so really, the goal here is for you to understand exactly what I'm saying and follow line by line every derivation. So we're going to be interested in two main types of situations. We're going to be interested in systems that are described by some Hamiltonian, h of t, and the context we'll be interested in is basically twofold, split between Dima's lectures and my own. The first kind of trivial case is where h of t actually has no time dependence, so h itself is time independent, and that's the main case that we'll focus on in my lectures. And the second case, which is also particularly interesting, is where the Hamiltonian returns to itself after a period given by capital T, and this periodically driven system goes under the moniker of a Floquet system. And that's something that Dima will introduce in detail. So just to make sure that we ground ourselves in some physical system, or to keep some Hamiltonian in the back of your mind so we're not doing things super abstractly, an example Hamiltonian you can think about is maybe a one-dimensional spin chain. That's a context where lots of physics have been studied in the context of many-body localization. So we can imagine, for example, a Hamiltonian describing a nearest neighbor interacting spin 1/2 chain in one dimension. Sigma are Pauli spin 1/2 matrices. Jij is the nearest neighbor coupling strength between them. It can either be uniform or does not have to be. And of course, we can imagine having, for each of these spins, in addition to the interactions between them, we can have a magnetic field on HI in some direction. So all of the physics I'll be describing is much more general than this, but at least something to keep in the back of your mind so that we have something tangible to touch onto is a simple one-dimensional spin chain like this. And for such a model, or in general, for any models of strongly interacting quantum many-body systems, the lore of quantum statistical mechanics is very simple. It says that for such systems, so long as they are not integrable in general, we expect the system to go to equilibrium at late times. So that's basically the lore, It's kind of the unifying feature of all strongly correlated quantum mechanical systems. The lore of quantum stat mech is that we expect the system to go to equilibrium, to equilibrate at late times. And what I'd like to explore in the next few minutes is what precisely does this mean? What precisely does this mean? Question mark. So let's set up a little bit of formalism. So let's imagine that we represent, so we will hope to follow our nose within this definition and get to sort of a really clean-cut definition of quantum thermalization in an isolated many-body system. In general, we'd like to represent our state, since we're not always going to work with pure states, with a density matrix rho. You're all certainly familiar with the density matrix, which has certain properties. Rho dagger equals rho. The trace of rho is our normalization condition. But most importantly, within the context of many-body quantum dynamics, one can recall that time evolution of such a density matrix, so if one starts with an initial state density matrix given by rho at time t equals 0, to figure out what rho is at time t, we'd like to conjugate with the unitary that corresponds to time evolution, e to the minus iht over h bar, e to the iht over h bar. Okay? So this first year high school quantum mechanics. Time evolution within the density matrix picture.
Where did you go to high school?
No, they teach you well in China. I'm just kidding. Sorry. I actually grew up in Oklahoma.
Yeah, I could raise my kids in Oklahoma.
Chance. So, when we say that a system has thermalized, when we say that a system has thermalized, let me start by emphasizing what is not the meaning of this. When we say the system is thermalized, we do not mean that rho at some late time t, okay, the density matrix at some late time t, has reached the quote-unquote equilibrium density matrix for the full system. And let's just recall from StatNet, from your first year StatNet course, rho equilibrium, of course, what I mean over here, is something like 1 over the partition function, basically the Boltzmann minus mu n dot dot dot, exactly what we learned in terms of equilibrium state. So naturally, we think about quantum dynamics for a system. So we start out with a system that may not be in equilibrium. We evolve that system in time, and we get to some late time density matrix. The meaning that the system has reached equilibration is not what you might naturally expect, which is that this density matrix is now equal to the equilibrium Boltzmann ensemble density matrix rho equilibrium. That is precisely not what it means. Why is that not what it means? So we can ask the question. That seems like a pretty natural definition. You said the system went to equilibrium. So why is it that the density matrix of the system does not look like the equilibrium density matrix for the full system? The first reason, of course, is that time evolution in quantum mechanics is unitary. And thus, by definition, reversible. Reversible in what sense? In the sense that no information about my initial state is lost. When we think about thermalization, when we think about reaching equilibrium, the intuition is that if you have a many-body system which has two different many-body systems that share the same conserved quantities, after a late time, it's very hard to tell these two systems apart. That information is lost about that initial condition that led you to this final state. But because time evolution is unitary in quantum mechanics, no information is ever lost about the initial state. And in fact, of course, one can simply evolve backwards in time, or use minus the Hamiltonian and evolve forwards in time to be able to re-get the initial density matrix rho naught. So what does that mean? So what exactly? So given that quantum mechanics has time evolution as unitary and no information is really lost, where is the information going? Or at a late time, we still have the sense that it should be very, very hard to tell the difference between two states that nominally started with different initial conditions but have the same conserved quantities. What ends up happening, of course, is that information, instead of being lost, is hidden in very non-local correlation functions at late times, and is encoded in the entanglement structure of the final density matrix. So despite the fact, this is how we reconcile these two facets. The first is that quantum mechanics is unitary, so no information is lost. The second is the fact that, despite the fact that it's unitary, we have the sense that telling states apart at late times is very hard, and the reason is that this very hard corresponds precisely to the fact that the information about the initial state under time evolution of a strongly interacting system ends up being hidden in very non-local correlation functions or the entanglement structure of the final state. And most importantly, to detect this hidden information, typically then one requires access to non-local observables or non-local correlation functions, possibly extensive in the number of operators, and this makes things very hard. So, given that this is not what we want for our definition of thermalization, let's now be more precise and give what we'd like to use as the definition for thermalization. So, in the context of the next couple of lectures, thermalization, or a quantum mechanical system with many strongly interacting particles that achieves equilibration or thermal equilibrium, has the property that the full system, the full many-body system, behaves as a reservoir, or effectively a bath, and the thing that thermalizes is subsystems. And all subsystems are the degrees of freedom that thermalize. So we'll break this down in detail and write out a couple of equations that put this on very, very precise footing. But to start off, what this means is that the question of does it thermalize, I'd like you to think about as being mapped onto it as, is it a reservoir for itself? So that's the definition that I want you to keep in the back of your mind. I promise we'll make it precise in just a second. And already, maybe with a little bit of premonition, many-body localization, or localization in general, will precisely be the failure of this. Where a many-body system does not end up being a good reservoir for its own subsystems. So, it turns out, as you can already see, this distinction between a system that's many-body localized and a system that thermalizes is a sharp distinction. There exists a phase transition between systems that thermalize and systems that many-body localize, and that phase transition, for example, can be controlled by parameters in an experiment, like Emmanuel's experiment, or in theory, we usually utilize disorder to control that transition. But perhaps the most important caveat, and what makes us want to define things a little bit more precisely, is the fact that, like all phase transitions, the distinction between many-body localization and thermalization is only sharp in the thermodynamic limit. It's only sharp as we take the limit of very, very large system sizes and very, very limited times. So this is cause for us to be, yeah, please.
What do you mean by sharp?
There's only sort of a transition and not a crossover. At any finite size, there's a sort of a crossover that's actually smooth if one zooms in hard enough. Good. So let's now give the three-step method for defining thermalization. So if one wants to figure out whether a quantum many-body system thermalizes, one naturally follows these three steps. The first step is one should index all the conserved quantities of the system. The reason why one wants to start off by indexing all of the conserved quantities is that this is the stuff. These are the things that the system can actually be a reservoir for, right? if you have objects that are not conserved in the system, there's no notion where we say, actually, once this amount of energy moves from one region to the other, that has to mean that the original region has less energy density. So we'd like to think about conservation laws, and thinking about conservation laws tells us the stuff that the system can actually be a reservoir of. So let's ground ourselves a little bit. Examples of this that you're very familiar with, of course, especially in the context of static Hamiltonians, total energy is always going to be a good conserved quantity. So it's always something that we'll be able to think about the system as being a reservoir for. It turns out, in the context of what Dima is going to talk about, for driven systems, total energy actually does not end up being a good conserved quantity, but at least for systems where there is no time dependence in the Hamiltonian, total energy is conserved. Other things that you might be familiar with are things like particle number conservation, which of course is conjugate to the notion of a chemical potential. Other things like total spin, etc. But you'd like to start in your first step by indexing those objects that are conserved inside your system. And that, of course, will precisely define what we think of when we talk about the equilibrium density matrix. There will be some density matrix that satisfies, that looks like e to the minus beta h. That beta is really associated with energy density, minus mu n. That mu is really associated with the fact that we have a conservation of particle number, and so on and so forth. Step 2. We're going to imagine that we break up our system, which has n being the total numbers of degrees of freedom, into two different pieces, which I call B and S. B stands for what I think of as the piece of the many-body system that behaves as the bath. And it's so defined because S I think of as the subsystem that I will be interested in asking questions about. Remember, we define thermalization in terms of subsystems. The full system does not thermalize, it is subsystems that get thermalized by the full system. So the subsystem S is what we're going to think about. And we will take the limit where we have the number of degrees of freedom of the entire system and the size of the bath to infinity, but we will hold the subsystem fixed. That's the limit I'd like to take. Turns out, more recently, there's questions about strong and weak versions of thermalization, where there's questions about whether or not S can scale extensively, but certainly we're working in the safe limit, that known as weak thermalization, where we take n and b to infinity, but we hold S fixed. Good? So now, let's figure out the time evolution of the full system. For the full system, the density matrix, rho n, of T, as we already wrote before, evolves according to e to the minus I h n t over h bar, rho n at time t equals 0, e to the I h n t over h bar. Yeah, please?
When you take your bath, like when it goes to infinity, does the physics at the boundary change?
Is the physics of that? Oh, no. You can think about this. It's always locally interacting, for example.
Okay.
So now here's a very important thing that you'll remember from your quantum mechanics class. we talked about the evolution of the full system, but we defined thermalization as fundamentally a property of subsystems within the full system. So we better now look at the density matrix of the subsystem. And the way to do that, of course, is to simply trace out all of the degrees of freedom of the bath, such that one gets the reduced density matrix of the subsystem. So we define rho s at time t, the quote-unquote reduced density matrix of the subsystem, as tracing over all of the degrees of freedom of the bath of the full density matrix rho n. And here, I'm going to write the same definition that we have over there, but now in terms of an equation. Actually, maybe it's important enough that we'll do it back over here. So what we mean when we say thermalization, we mean that in the limit of very late times, in the limit where we take system size to infinity, the order of limits here is important, the reduced density matrix rho s of t for a subsystem is precisely equal to the equilibrium density matrix on that subsystem given whatever conserved quantities we had. So there's a temperature, if we have a notion of conserved energy, there's some set of chemical potentials, for example, etc. I haven't exactly told you precisely what this equilibrium density matrix is yet. So let's make that precise. That is given by the limit as n goes to infinity, trace over the bath rho n. And here, when I write rho n equilibrium, I'm precisely writing down for the entire system the Boltzmann ensemble. Okay, let's really break this down a little bit. So what we're saying is that at large, take a large system size limit and a late time limit, and we say that the subsystem, the density matrix of the subsystem, is the object that looks thermal. It looks thermal with respect to what? With respect to anything that the system can behave as a reservoir for, which doesn't change because it's a conserved quantity. All of these properties of the system, the energy density of the system, for example, will not change as a function of time. And we figure that out by tracing out the equilibrium density matrix for the entire system, where we trace out the bath degrees of freedom. And rho and q is precisely given by what you would really expect to be defined with respect to quantum static. Let me emphasize a particularly simple limit here. In the limit where there does not exist any conserved quantities, for me, for the static situation where there's no dynamics, there's no time dependence to the Hamiltonian, you will always have energy density at very minimum. But I mentioned that in the context of periodically driven flow K systems, for example, even energy doesn't have to be conserved. So this particularly simple limit is that when there doesn't exist any conserved quantities, this equilibrium density matrix is simply proportional to the identity. Good. So again, what we're saying here is that the thing that thermalizes when people talk about quantum thermalization in an isolated many-body system is a subsystem, and the way to figure out how thermal your subsystem is for a given many-body Hamiltonian is to look at its conserved quantities, write down the Boltzmann density matrix, trace out your degrees of freedom that you call the bath, and when you look at the reduced density matrix, if these two match on, that's exactly what it means to have a system that thermalizes. Yeah, please.
What's the difference between saying it like this and then saying the rho st at A times will be like will look like the Boltzmann density matrix? Like you're saying the rho st.
Yeah, okay, exactly. But it's not well times looks like the Boltzmann density matrix for the subsystem. Because when I think about an energy density, if the energy density is over the entire system, I don't want to say, you can imagine having a subsystem which initially at time t equals 0 has a large amount of energy. Somehow it's hot relative to the rest of the system. So if you said, okay, let me just look at the amount of energy density here and define the thermal density matrix with respect, the equilibrium density matrix with respect to that, and see whether my late time evolution gets there. The answer is it won't. So we have to define it in terms of this trace because we want there to be an overarching system that's thermalizing the that, and the conserved quantities of that system are the objects that are well defined. Good. Good question. Good. This is pretty important. Is everyone following? I see lots of nods, so I hope that's the case. Excellent. So, a couple of remarks. The first, maybe important remark of making this notion of thermalization in an isolated many-body system precise is that really we have equilibrium thermodynamics in the context of quantum stat math emerging from an isolated many-body system's own dynamics. And the second is really more of an expectation than a statement. When we say that a system, a many-body system, thermalizes, we expect that to be a pretty generic statement. We expect that not to be, with many caveats. It thermalizes if the initial state satisfies this condition, if the dynamics satisfy this condition. We have the expectation that for a system that thermalizes, basically all subsystems, and all initial conditions satisfy this property, this definition of thermalization. Okay? So we'd like to not, we have a general definition of quantum thermalization of a many-body interacting system. We'd like to have it that this is basically satisfied for all different subsystems and all different initial conditions. Yeah, please. Yeah, it doesn't matter. Anything. You can have the bath in different states, the system in different states, whatever you want. You can partition the system into different, it doesn't have to be well defined. You can partition the system into a very weird set of degrees of freedom it shouldn't have. This motivates maybe one of the most powerful consequences of quantum thermalization, known as the Eigenstate thermalization hypothesis. The Eigenstate thermalization hypothesis, or ETH. Formulated, I think, actually it was probably formulated earlier, but certainly by Deutsch in 91 and Trednicki in 94. Maybe it's where it was first written down in this language. So you can ask a natural question that literally extends from this hopeful expectation, which is if we basically want all subsystems and all initial conditions to thermalize, what about many-body eigenstates? What about many-body eigenstates?
But should this subsystem should be much smaller than the whole system?
Yeah, what I've written thus far is I've assumed that it's going to be true because when I take n and b to infinity, if I hold x fixed, then I'll always have that property.
So all finite subsystems?
That's right. I think that's not. Yes, and that's something that typically people call weak thermalization. It turns out there's a stronger version of this called strong thermalization, where there's a question whether or not, in fact, you can basically have S as large as half the system, where this basically still holds. And that's, actually there's some numerical evidence that the strong version of that actually also holds, but I think it's less clear.
So in that picture, the degrees of freedom of the subsystem scale with the degrees of freedom of the bath?
No. No.
The picture you see-
Imagine that you have basically 50 spins here, and then you have initially, I don't know, 1,000 spins, and then you keep your number of spins 50 over here, and you take this to infinity.
But you said something about half.
Yeah, so that was an answer to his question, which is basically that for strong thermalization, there's a question which is, there's conjecture, maybe I would say it that way, where as so long as the subsystem is smaller than half the size of the full system, in this case it would scale to that, then that notion of thermalization that I've defined over here still holds. That's been numerically tested in certain models, but I think is not, certainly not as safe a definition as what we're using here. Good, so there's a natural question motivated by this expectation, which is, what about many-body eigenstates? These are certainly valid initial conditions that I could have my full system be in. I'm allowed to start in a many-body eigenstate. But of course, the many-body eigenstate has no time evolution. The many-body eigenstate, usually we're thinking about time evolving the system, but the time dynamics of a many-body eigenstate are trivial because there is no time dynamics. So let's follow our nose and try to look at the definition and see what the consequence of satisfying this definition would mean for many-body eigenstates. So what I mean by that is let's specifically consider the case where we have a Hamiltonian, and the Hamiltonian has eigenstates indexed by n, where there's an associated energy En n. And we can start our system in a many-body eigenstate, in which case it has a corresponding density matrix that's simply the ket bra, the projector into this many-body eigenstates, the definition of the density matrix. And we know that, of course, if we wanted to define what we mean by a subsystem for a given many-body eigenstate, we'd still do it in the same way. We'd start out with this density matrix of the many-body eigenstate of the full system, and we trace over all of the degrees of freedom of the bath. It's not at all different from what we are doing over there. And if these states also satisfy the definition of thermalization, this means that, in fact, without, now, the key difference between these two equations is that there's no time dependence here, because the many-body eigenstates themselves do not have time dependence. But if it satisfies this definition, then one expects that any subsystem of a many-body eigenstate looks thermal. So that's precisely what the statement of the eigenstate thermalization hypothesis is. So let's write it out in words, what we've written out in equations. So we're sort of going the opposite direction in this case. So the statement of ETH is that in each many-body eigenstate, all subsystems are thermal. The H in ETH stands for hypothesis for a reason. So it turns out this statement is extremely hard to prove. So it is, at its core, a hypothesis, a very powerful hypothesis. So it's extremely challenging to prove, extremely difficult to prove. But, and this is a pretty big but, I would say, it's been numerically tested for very, very small system sizes using exact diagonalization. So maybe this is a good point to emphasize one of the challenges of doing studies related to this type of physics. So I don't know how many of you are familiar with trying to solve for many-body ground states. It turns out that there are techniques in that context where one can solve for extremal eigenvalues and eigenvectors of a matrix, aka the ground state of a Hamiltonian, using techniques that, like Langshaw's, which are extremely powerful, but it turns out to test things like ETH, or to really ask questions about quantum thermalization and localization, it turns out one has to know about properties of the entire spectrum, not just about the physics of the ground state. So there's a much more limited set of numerical and computational tools that apply to this type of question. The safest one is using exact diagonalization of a full Hamiltonian, which simply scales terribly. And that means you're limited to very small system sizes. There's some generalizations of DMRT to excited states, which work in certain contexts, but one has to be a bit careful about convergence. Okay. So it's numerically tested, it's a very powerful hypothesis, but it's extremely difficult to prove. And in some sense, maybe one very important perspective is that if true, this is the reason why simple unitary time evolution can look like it's chaotic or can look thermal. It's not by having dynamics, unitary dynamics, that is chaotic, but because the eigenstates, which build up the many-body system, themselves are actually thermal at their core. Maybe a particularly nice side consequence of ETH is a nice way to understand non-equilibrium systems, or to understand a quench initial condition. So oftentimes what we've been thinking about is starting with an initial condition rho n of 0, which is not in equilibrium, so we usually say that's a quench initial state. It's an out of equilibrium state. And this notion of ETH gives us a kind of very pretty way to understand that idea of non-equilibriumness. Let's follow this. We can have any general density matrix. We can have any general density matrix expanded in terms of a double sum of eigenstates. What I mean by that is that we have our eigenstates n here, n and m, both index full sets of the many-body eigenstates of the problem. Any density matrix can be expanded as rho and m and a projector onto m. N and m is just true. So all density matrices, all quench initial conditions, whatever it is, can be represented like this. But we've already made a pretty deep statement, or a very powerful statement, using ETH. Let me demonstrate some of that power. It turns out that in this expansion of a general density matrix, if ETH holds, if the eigenstate thermalization hypothesis is true, then all diagonal elements, so anything that looks like an n within this sum, are already thermal. So we start with a quench initial condition. We can write that as a double sum of eigenstates. But it turns out if we believe ETH, then this is a sum. All of the diagonal elements in the sum are already thermal in the sense that subsystems look like the Boltzmann ensemble. And of course, What this means is that, maybe the implication thus, all of the non-trivial out of equilibriumness of the quench initial condition lives in the off-diagonal components of rho and m. Diagonal components of rho and m. So this is what people mean when they say, so you'll hear oftentimes in talks, people talk about, oh, we have an out-of-equilibrium system, and the reason for this is we have some off-diagonal coherences of the density matrix. What do they mean when they say that? Precisely this, that if you expand their initial state in a double sum over all eigenstates, all of the diagonal elements are already thermal, if we believe in ETH. And thus, any of the non-equilibriumnesses of the initial state really lives in the off-diagonal components, where people often talk about that as off-diagonal coherences of the density matrix. And if ETH is true, thermalization is precisely the dephasing of these off-diagonal coherences. It's that these off-diagonal coherences basically lose their phase coherence that ends up making them this special initial out-of-equilibrium state. So thermalization is basically directly akin to dephasing of these off-diagonal coherences.
Dephasing meaning that they evolve at different frequencies?
Yeah, exactly. They evolve at different frequencies, and precisely because you know that the eigenstates evolve in the same way. They evolve at energy differences Em minus En multiplied by time, and now whatever initial sort of ratio of phases you had is going to go out of phase and look totally destructive. For a finite size system, of course, all of these will come back to each other after an exponentially long time in the number of elements there. But once one takes n to infinity, it never comes back. Good question. Good. So yeah. So I'm so sorry.
So does that mean that for all the many body eigenstates, the reduced density matrix of a subsystem is the same for all of them? Does the theorem?
Nope.
No.
The key is that, for all of these, subtle, right? So we have the equilibrium one, right? The rho s equilibrium depends on something about this density matrix, which, for example, is its energy density. So, if you have two different eigenstates at two different energy densities is conserved, so it'll be an equilibrium Boltzmann density matrix, but at the right energy density associated with your initial many-body eigenstate. That would be super boring if that were the case. Good. So let's sum. Yeah, go ahead.
I think this is about the phasing, but I usually assume like if you have the phasing, you also have a map that you don't know about, and that is what causes the phasing.
But in answer to John's question, that's okay. We usually assume that, but really, I think I'm thinking about the phasing in a slightly different way here. It's that if you have a big density matrix, rho and m, the off-diagonal elements, the fact that you have a specific out-of-equilibrium initial condition is related to relationships between each of these off-diagonal elements. But each of these off-diagonal elements evolves as e to the minus I, En minus Em t over h bar for different energies En and Em. So the relationships that define her initial out-of-equilibrium situation precisely, loses, whatever those relationships will be lost as you evolve, as each of those elements, E and M, rho and M, evolve with a different phase, determined by the energy difference En minus Em. So that's what I mean by dephasing. Not, I think, dephasing in the sense that what I mean is loss of the specific relationship that characterized the off-diagonal coherences to lead to a specific out-of-equilibrium initial state. not dephasing in terms of like T2 or T2 star when I think about, I don't know, spins coupled to a bath. So maybe let's, I don't know, phasing quotes. Clear? Wonderful. Good, so let's summarize what exactly we mean. So we've tried to put on a little bit more solid footing this question of what exactly it means for an isolated quantum many-body system to thermalize. So this question of does it thermalize can have two answers. Yes and no. In the no case, it turns out there are a number of situations that some of which you've already heard about. Systems that are, quote, integrable, which have a number of conserved quantities that scales extensively with the size of the system, don't thermalize, simply because those conserved quantities constrain the equations of motion to never really forget our initial conditions. The slightly more generic case in the sense that it's perhaps stable to perturbations is the case that we'll start to discuss in just 1 second, is the case of many-body localization or localization in general. Okay. And the difference between systems that thermalize and systems that don't, they're separated by a phase transition defined precisely by whether or not the reduced density matrix satisfies the definition that I gave in the late time large N limit. Most of the systems that you'll be familiar with do thermalize. But in this context, so this is, maybe generic, strongly interacting many-body systems. But there's an important sub-distinction in this family of yeses, which is to ask how fast this system thermalizes. And here, I think it's really important to contextualize within experiments like what Emmanuel does, which is to ask, does the system thermalize at an experimentally accessible timescale? So, at an experimentally accessible timescale? If it does, then you can definitely distinguish between this system and a system that's localized. Or does it thermalize on a timescale controlled parametrically by parameters of the system on an experimentally inaccessible timescale? That's also possible. Some examples of such systems are pre-thermalization or pre-thermalizing systems, another topic that I suspect Professor or Dr. Bima Bonham will talk about in detail. And despite the fact that the true theoretical distinction between systems that thermalize and don't is split by a phase transition, within an experimental context, it may be very, very hard to distinguish between systems that thermalize at accessible and short time scales and inaccessible and long time scales, but strictly speaking, the distinction between these is only a crossover. Are there any questions? Okay. Yeah, go ahead.
You talk about crossover phase transitions, but I guess you talk about it later. How do you detect?
Yeah, so for all intents and purposes, in an experiment, it would be very, very hard to distinguish whether or not this really, was a transition between a system that didn't thermalize because you couldn't see it thermalize on an experimentally accessible timescale. But actually, if we believe, whether or not the experiment gets to that timescale, there can be a well-defined notion of thermalization in the system where one believes that it's parametric controlled by a very long timescale in some parameter of the problem. In that context, there's no strict thermodynamic difference It's really, one is short and one is long, and that's why I call it a crossover. But I want to emphasize that within experiments, it's important to realize that sometimes it may be very hard to be able to distinguish if one has such a long emergent timescale, which is why people are really pushing to have systems that can really coherently evolve for many decades of time with respect to the local energy scale within the Hamiltonian to be able to try to rule out these distinctions in cases where we don't know the answer. Please. You first, no?
Yeah, that's very quick. Sorry. So there's a case where a row where you have off diagonal components that are not zero. Then it's currently mapping on eigenbasis, but ETH still says in this basis that n with the bracket.
Okay, let's be very careful. So what does ETH say? ETH says that density matrices, which are made out of many-body eigenstates, so you have a pure state, many-body eigenstates a pure state, but I can make a density matrix out of this pure state that's, kept broad n, right? That object looks like it has a, that object looks like it will have subsystems that look thermal. Okay? So the statement about, I've made no statement about M and N over here, right? Things that look like M and N do not look like a density matrix associated with a pure state that began in a many-body eigenstate. These are elements of an expansion that I can write a density matrix down in terms of its basis, Mn, but the only thing that ETH talks about is the diagonal elements of this object. Okay? And then the statement about dephasing is precisely that the relationship between the values of the rho and m, which sets the particular nature of the out of equilibrium initial state, gets dephased over time because they evolve at different rates, En minus En. Good?
You said that in a given many-body eigenstate, all of the subsystems are thermal.
Yeah.
The question is whether they are characterized by the same temperature for a given many-body eigenstate.
Yes. If ETH holds, then the answer is yes. That would be that's right. The whole point is that subsystems of that are basically thermal with respect to each other. So independent, I have a many-body system, I put an eigenstate, and I trace out different paths. You pick any subsystem you want, however weird and filamented it looks, and you basically find that it should be described at the exact same equilibrium voltage. Yeah?
Your definition of you wrote that definition respect to long times, but if the many-body system is already in an eigenstate, then the density matrix of the subsystem has no evolution, right? It's already come up.
Yeah, that's exactly right. Sorry, let's emphasize that for 1 second. So, I wrote down that in general, when one thinks about time evolution for an initial state, so the key thing is there's 2 different initial states, right? You can have an initial state which is not eigenstate, and then you can have an initial state which is eigenstate. In the not eigenstate case, we take rho at time t equals 0, we evolve it with our unitary time evolution, and we get rho of t. And then when we look at rho s, the subsystem, that requires us tracing over the degrees of freedom of the bath of rho of t, which has been time evolved forward. And the statement that we make about the definition of thermalization is with respect to this 2. For an eigenstate, we say, well, the density matrix of the full system looks like this. And note, there's no user u daggers, because as you say, there is no time evolution. So the rho s object that we look at is simply a trace over the back of this density matrix of the system, but we still ask about the properties of the reduced density matrix of the subsystem, rho s, and whether or not those satisfy the definition that we wrote up. Okay, so I think this probably is a not bad place to stop, I guess, since it's 6. Tomorrow morning, we'll continue on defining localization. I'll start by defining Anderson localization, then move to an intuition for many-body localization, and then I hope to give a very quantum information perspective on what it means to have a many-body localized system in terms of storing quantum memories and having coherences in a quantum many-body system. All right, thanks a lot. Yeah.
I wanted to ask experimentally, what's the sufficient condition to prove that your system has thermalized? Because if you just measure some local quantity, it may look thermalized even though the system hasn't thermalized. Do I really need to have the full density matrix of my system and then take, trace of many subsystems and see that?
I think that there's different stringencies for that requirement, but actually the most natural requirement is exactly what you said. Initial condition that's certainly out of equilibrium. And look at some local correlation functions. This can be, autocorrelation functions of a spin degree of freedom, or density correlation functions in a system of fermions. Whatever it is, you look at the evolution of that as a function of time, and you ask whether or not that correlation function reaches a value consistent with its thermal expectation value.
But like higher correlation functions may thermalize later.
It's a very, very subtle question. Well, you asked it. So it turns out one can think about this, and that's a subtle question. So let's imagine really taking his question and moving forward with it. So let's imagine that we start with something like a 2-point correlation function. Okay. So it turns out, we say that we have some 2-point correlation function, and let's imagine that, I promise this will be useful. I mean, it sounds like it might not be useful, but it's useful. So let's imagine we have a 2-point correlation function and really understand what he's asking. He's saying that maybe I start with a state and the 2-point correlation function looks like it lives at some value. And I evolve as a function of time and I say, oh, okay, the two are going to exhibit some non-trivial dynamics, but eventually equilibrates to, whatever value one expects it to equilibrate as. And let's define that time scale of equilibration T eq 2. Okay? You do the same thing, and you basically look at this for many, many different 2-point correlation functions. And that nominally defines some expectation value, some expectation for the time scale that 2-point correlation functions in a thermalizing system reach thermal equilibrium. But now he says, okay, what if I now look at a 3-point correlation function, or a 4-point correlation function, all the way up for a finite size system to an n-point correlation function? It turns out that you naturally expect for a 3-point correlation function that in fact the time scale it takes such a slightly more complex object to thermalize will be a little bit longer than the 2-point correlation function. Let's define that as T equilibrium 3. And even longer for a higher body correlation function. So when we think about thermalization, the definition that I have is fundamentally a very local definition. Right? I define things with respect to subsystems, and that subsystem may have some finite size, so there may be some finite number correlation function that I'm looking at, but I'm taking the thermodynamic loop where n goes to infinity. But actually, in fact, you are allowed to ask a question, which is, if I keep increasing the order of the correlation function, what exactly happens to the timescale of thermalization, or the timescale of equilibration, and it will get longer and longer and longer. And in some sense, the timescale where even n-point correlation functions do not distinguish between two different initial conditions is something which is known as scrambling. So I don't know if you guys, it's something that has been word that's been tossed around a lot lately. But this notion of scrambling is precisely, in some sense, when we want to make analogy to thermalization, it's a situation where two different initial conditions cannot be told apart from each other unless you make an extensive correlation function type measurement. But in general, this expectation thus is that there is some time scale which is for a many-body system, the scrambling time scale, and that time scale is what happens when you ask about extensive correlation functions. But everything that I'm talking about is local, so in terms of my definition with respect to sort of a weak thermalization of subsystems, I'm really thinking about correlation functions that have some finite size taking n to infinity.
Yeah, but I'm going to distinguish between.
Sorry?
But which one do you pick, like between this finite?
You could pick different 2-point correlation functions.
Yeah, sure. So I'm saying,
one
basically,
2-point correlation function is thermalized, another one maybe not thermalized yet. So I think it's like what you said. I mean, the best we can say is that it's consistent with thermalization. But to prove thermalization actually of the subsystem of, let's say, 100 particles with 100 slice system within a system of 1,000 or 10,000, that's difficult.
Yeah, I don't know, I guess the question is, again, I'm not sure what one, okay, I certainly agree with Emmanuel, I'm not, but my argument would, my statement would be, I'm not sure what it means by prove in this case. I would say, if you take a look at many, many different two-point correlation functions in a system, and you find the average timescale on which they reach their equilibrium value, then that's a well-defined notion of local thermalization of the system. But it's not going to be the same as if you define, there's actually, look at the same thing for a three-point correlation function, but actually there's some order one number that differs between these, and I don't care. That order one number sort of doesn't impact the statement about whether or not the system is thermalizing at a local state, right? So you can pick whatever size you want, as long as you don't allow it to scale with the system size. Good question.
So does this no means that all things belong to this category breaks the ETH?
Yes, that's right. That's exactly right. So in this no category, basically, Eigenstate, ETH is broken precisely because the system doesn't thermalize. That's right. That's exactly right. Sorry, I should have said that. Any other questions? Stomachs are grumbling. Okay.
The rest over dinner.
Sorry?
I said the rest of the questions can come with you.
Exactly. Perfect.
This time.